Right. Okay. Hi, everybody. This is Simon Wong. I'm with College of Professional and Continuing Education at the Hong Kong learning model for bypass optimizations. And at the end of this presentation, if you have any questions, feel free to email to me or you can ask me any questions, right, about this paper, right? Okay. This is my email address, simonwong189 at gmail.com. I will give you a background and talk about research objectives and what insight I've got from the literature review, and talk about the bypass optimization algorithm. And this algorithm is based on machine learning model. We talk about the reliability and accuracy of the algorithm and give you concluding remarks and suggest the future work. Right. Now in Hong Kong, when a call center receives an emergency call, a source nearest to the incident's location may set out a road transport for emergency services towards the incident's locations. The incidents may be a fire, a crime, or accident, right? And the road transport for emergency services include ambulance, fire vehicle, and police car. Right? And in Hong Kong, the ambulance and the fire vehicles are parked in a fire station, while the police car are parked in a police station. So when the call center, right? When the call center, I mean, that is emergency call centers, right? We receive an emergency call requesting a transfer for emergency services, right? They will find out the nearest fire station or nearest police station. And what I mean by the nearest means that station is nearest to the incident's location, right? And there's a performance pledge by Hong Kong government, right? And this performance pledge is to make sure that the time when the emergency call is received, and the time, right, for the arrival of a road transport for emergency at the incident location, right, these two times should be within 12 minutes, right? So this is a performance pledge by the Hong Kong government, right? To ensure this performance pledge, the fastest path, which is also in this case, which is also the shortest path, and we know that the fastest path will not be the shortest path because there's a speed limit on the road. How we know that? Okay, with the speed limit. So in some cases, right, the fastest path will not be the shortest path, but because this transport for emergency services has no speed limit on certain roads. Right? In that case, we think that the fastest path is also the shortest path, right? And this fastest path from the source to the destinations, which is the incident locations for the road transport for emergency services, can be planned. And the Detouring algorithm, which is a well-known algorithm for finding out the fastest or shortest path, right, can be adopted, right? And this paper about this Detouring algorithm, right? I think most of you are familiar with this, right? Now, the research problem is there's a major obstacle to the performance pledge. That obstacle is the frequent unanticipated occurrence of traffic congestion on the planned plaza pass in some Hong Kong roads especially in heavy traffic congested areas. So while the design of many of these roads is not feasible for air transport or sea transport. So detouring is unavoidable when traffic congestion is on country. So on top of the planned fastest path, backup routes for the detour from the planned path are set up beforehand. And these backup routes are called bypasses in my paper. Okay, and to set up these bypasses is to save time for searching for time-effective detours due to frequent unanticipated traffic congestions in Hong Kong road conditions. Right. So this is a planned fastest path. This arrow indicates that. And here, if this is congested, right, so the road transport for emergencies cannot go through this fastest path, then it's go through the bypass. So to make everyone understand what I mean by bypass, I need to define some terms like a block. Okay, so a block is a portion of road between two junctions. So in this picture, you see a block AB, right, which is between the junction A and junction B. Need to think about this one is also a block, right? A1 and AB, block A1 and AB. So the junction at A1 and the other junctions at B1, right? All right. So this one, right, the block, right, from A to B, is the planned block. Okay, planned block. Okay, so the possible bypasses for this planned block, right? I use this notation AB, right, with a square bracket here. Indicates the block, right, between the junction A and junction B, right? So these are the possible bypasses for the planned block AB, A1, B1, B, right? This is one possible bypass, right? Okay. Now the other possible bypass for the planned block AB is A2, B2, B, right? Now actually there are many other possible bypasses, right? And in this paper, I propose the area to search for the optimum bypass. Okay, and I will explain what optimum bypass means in a minute. So to make these algorithms work, I suppose the Internet of Things devices are installed at each block of the road in heavy traffic congested areas of Hong Kong. And the sensors of the IoT devices are used to collect the transit time of each vehicle passing through the block. And these large amounts of transit time formulate a big training data set for machine learning to generate a probabilistic model of traffic congestion. So this research objective is to design a bypass optimization algorithm that adopts the machine learning model to generate the probabilistic model of traffic congestion at some roads, and construct the optimum bypass structure based on the probabilistic model for a road transport for emergency services to detour to avoid traffic congestions and for efficient detouring. Literature review. Right. Now, to conduct a literature review, I set the following inclusion criteria, right, for the literature search. And I searched through some search engines like Google, Progress, Scopus, Web of Science. And this criteria includes the study published up to this year when this article was prepared, and the study related to the status of fastest path with bypasses for a road transfer for efficient routing. In the trying to search for this, where there were no results returned, right? So indicating that no previous studies thoroughly explore bypasses for a road transfer for efficient routing. And I use less stringent terms to search. Right? And for example, in Scopus, you see this symbol, right? We see the title, abstract keys, right? I use these keywords, right? Shortest path, fastest path in road transport, right? So I skip the word bypasses, right? And I found some previous studies. For example, the studies indicated in this number, right, 2 to 5, right, focus on the shortest or fastest path for road transportation instead of bypasses. So let me talk about the bypass optimization algorithm using a machine learning model. So with the transit time of each vehicle passing through a block, the mean transit time x bar, I use x bar to indicate the mean transit time, and the standard deviation of the transit time sigma, right? I use this sigma to stand for standard deviation of the transit time, right? This time, mean transit time, and standard deviation of the transit time can be obtained. And based on this data, the fastest path from the source to destination can be planned by using a Detouring algorithm. And I suppose the fastest path at the source, denoted by S. S means the source, right? And it's at the junction here, right? Each of these nodes indicate the junction, right? Junction, and between this node 0, I call this node of 0, this node of 1, right? This is a block, right? Okay. And you can also think this is also a block, right? Node of 0 and node of 2 also a block, right? And suppose that this is the fastest path, right? Node 1, node 2, so node 0, node 1, node 2, up to node of 4, right? Yes. Okay. The big train links data set, right, can be analyzed by binary classification in machine learning to classify the input data into one of two mutually exclusive classes. One class is no congestion, in which the amounts of transit time are clustered around x bar, which is the mean transit time. Right? The other class is congestion class, so in which the amounts of transit time are clustered around x bar plus 3 times sigma. Right? This is based on the 3 sigma rule of thumb, which states a conventional heuristic that nearly all values tend to lie within 3 standard deviations of the mean under normal distribution. And in this regard, the transit time that falls outside 3 standard deviations of the mean, right, is regarded as congested case and classified into the congestions class. So with the aid of a binomial logistic regressions classifications algorithm, the number of cases in either no congestion class or congestion class can be obtained, and therefore the probability of traffic congestion wrong at the block can be computed. I suppose a block between node of 0 and node of 1 is denoted by this one 0, 1, right, with a square bracket here, right? So we should block along the farthest path from node of 0 to node of 4. We have these blocks, right? 0, 1 block, 1, 2 block, 0, 2 block, 2, 3 block, 1, 3 block, 0, 3 block, 3, 4 blocks, 2, 4 blocks, 1, 4 blocks, and 0, 4 blocks. And the optimal bypass is search. Right? So what does it mean by optimal bypass? I'm going to explain that in a minute. Okay. So to locate the optimum bypass for the block between the junction A and junction B, all right, I call this block AB, right? Or AB block. Okay. So the following assumptions and notations are used. Now, AB block contains two junction blocks, right? For example, L sub 1 is block, L sub 2 another block. These are two junction blocks, right? Right. So you can think about this here between A and B. You have these two junction block. I call this L sub 1. Then another block L sub 2. Up to there's many two junction block. All right. And finally there's a L sub W. All right. Okay. So with the probabilities of traffic congestion, right? Row sub 1, row sub 2, up to row sub W. And suppose there are two possible bypasses for AB block, right? One with two junction blocks, right? This one, right? With the probabilities of traffic congestion row, right? I use this one, right? L W plus 1 sub plus W plus 1. L W plus 2 and so on, right? And these are the probabilities row sub W plus 1, row sub W plus 2 and so on, right? Until row sub W plus M. So while the other bypass with two junction blocks, this one, okay? L sub W plus M plus 1 and so on, right? Until with this probability of traffic congestion, right? And I suppose this is availability, which is 1 minus probability of traffic congestion, right? So based on the conditional probability, the availability for what? This means the possible one bypass. So array for one bypass is computed as follows. And this indicates the array of the planned path for AB block. While this part indicates the availability of the bypass for the AB block. So if this is not okay, then this one, right, indicates the availability. Okay. So this, right, these two together, right, added together means the availability, right, availability of the bypass for the AB block. Now, over here you see this is the availability for the other bypass, right? So the optimum bypass is the bypass for a block with the highest availability. So if the availability for one bypass is greater than the other one, we use the greater, we use that bypass with a greater availability, right? Now, and suppose this one, this symbol S, right? 0x is the availability for the bypass structure for the 0x block, right? So this means the block with the at the junction 0 and the other junction, right, as x. While this one PJX, right, indicates the highest availability between node of J and node of X, right? So the optimum bypass structure, which can be the optimal bypass or the concatenations of the optimal bypasses, right? So for this planned path, that can be one optimal bypass or concatenations of many optimal bypasses. And this is formed by computing as follows. So when x is equal to 0, so this availability is 1. So when x is 1, which is equal to the highest availability, because this is only, right, so between this is 1 with the highest availability between node of 0 and node of 1. While if there are many possible bypasses, right, between right node of 0 and node of x, if x is larger than 1, right, we need to find out the maximum in this case. Okay, so this is error, and I give you a scenario of how this algorithm works, and you have a better idea, all right, about how these computations work. Okay, so to search for the optimum bypass structure for the fastest path from node of 0 to node of j, right? Step 1 defines the optimum bypass structure for 0, 1 block. Then step 2 finds the optimum bypass for right 1, 2 block. And step 3 finds the optimum bypass structure for 0, 2 block, and so on, right? Until reaching the destination at node of 4, which is the destination, okay? Now, step 1, when x is equal to 1, the optimum bypass structure with this availability, which is the highest availability, right, for the block 0, 1. Okay, if we go back to here, right, go back to here, you see when x is 1, so this S is equal to P, right? The available bypass structure is the highest availability between these two nodes, right? Node of 0 and node of 1. Right? Okay. Now let me skip this. Now next, at step 2, the optimal bypass with the highest availability, right? P, right, between node of 1 and node of 2 is found. Right? Then step 3 is at this time, right, x is equal to 2, right? So you see, right here, x is 2. Previously, x is 1, okay? Now x is 2. And this optimal bypass structure with the with the availability, which is equal to the maximum of this, all right? So we've got, for this one, S01, which is found in step 1. While this one, right, P, right, 1, 2, which is found at step 2. And now, at step 3, we find this P02. Alright? So the maximum of this will become S02. Right? Then next, step 4. For step 4, we find P, right, 23. And step 5, we can find P13 is step 5. Right? And step 6, right, at step 6, x is 3. Right? The optimal bypass structure with x03, which is maximum of all these 3 figures. Right? So here, x01 finally step 1. Right? P, right, 13 find in step 4. While S02, right, find in step 3. Alright, and this one P23, sorry, 2P3 find in step 4, and find this one 13 find in step 5. Right, sir? Okay. Now we can find the maximum of this value and find the S value, right? So we keep on searching in this way, and eventually we can find the availability between node of 0 and node of 4, right, from the source to destination. This is the availability, and which is the maximum of all these values, and this will ensure the highest availability, right, for the bypass between node of 0 and node of 4, right, between the source and the destination, right? Now, let's take a look at the reliability and accuracy of the algorithm. The reliability and accuracy of this bypass construction optimization algorithm can be proved by induction. So the base case is x is equal to 1. So when x is equal to 1, right, we want to find, right, the bypass, optimal bypass, right, between log of 0 and log of x, right, which contains the two junction block, 0, 1, right? So the optimal bypass with this is 1, right? The availability for this is the highest availability between log of 0 and log of 1, right? Then next, when x is equal to, we want to find, right? We want to find the optimal bypass between log of 0 and log of 2, right? Which contain the bypass structure with the optimum bypass structure for, right? For 0, 1 block, and the optimal bypass for the two junction block, right? 1, 2, or the optimum bypass structure for 3 junction block, 0, 2, right? And the highest availability for the bypass structure for 0, 2, right, is this, right, which can be concatenation of these two optimal bypasses or one optimal bypass, right, with this P, right, or two, right, two optimal bypasses, and we get this S value. So the optimum bypass for 0, 2 for the block 0, 2 with S 0, 2 can be constructed. All right, now when x is equal to 3, right, the block 0, 3 can contain the bypass structure with the following: optimal bypass structure for 0, 2 block, and optimal bypass for the two junction block 2, 3, right? Or the optimal bypass structure for 0, 1, and the optimal bypass for 3 junction block 1, 3, or one optimal bypass between node 0 and node 3, right? So the optimum bypass structure for 0, 3 is S03. So this can be, right, one optimal bypass, right, which is here, or this guy, right, S01, S01, right, times this one, P13, P13 obtained here. So this can be the optimal structure between these two loop and one optimum bypass between node 1 and node 3. Or this one, right, the optimum bypass structure, right, between node 0 and node 2, right, this can be two bypasses, optimal bypass, or one optimal bypass with this one, the optimal bypass, right, between node 2 and node 3, this one. Okay, so this ensures the highest, right, which is the maximum. So this ensures the largest value among all these different possible, right, bypass structures, and we want to get the optimum, right? And finally, x is 4, right? We got all these different, okay, bypass structures, and we want to find out the bypass structure with the with the largest availability, right? So in this case, we can ensure that this bypass construction algorithm, right, can find the optimum bypass structure between the source and destination, right, with the highest, right, availability. All right. So This industrial shows that the proposal bypass cost optimization algorithm using the machine learning guarantee the optimal bypass structure with the maximum availability, where node of 0 is the source and node of x is the destination. Now, this proposed bypass optimization algorithm using machine learning can be evaluated in terms of its performance by numerical analysis using time complexities and simulation of detail cases, and stakeholders' acceptance of this technology. Right? Thank you.